We have been transmitting into space for over 100 years. Radio signals, television broadcasts, military radar, deliberate messages aimed at specific stars, all of it expanding outward from Earth at the speed of light. A sphere of noise growing by 300,000 kilometers every single second. Right now, the outermost edge of that bubble is more than 100 light years from here, washing over thousands of star systems, announcing our existence to anything close enough to pick it up. Nothing has answered. Hold that silence for a second, not as an absence, as a fact that needs explaining. Because the universe, by every calculation we've run, should not be this quiet. The math points somewhere completely different, and the gap between where the math points and what we actually observe is one of the strangest open problems in all of science. It's not a gap we've been ignoring either. The brightest physicists, biologists, astronomers, and philosophers of the last century have all taken a serious swing at it, and none of them walked away with a clean answer. That's worth paying attention to. Let's build the case from the ground up, because you really need to feel the weight of the numbers before the silence starts to feel strange in the right way. The Milky Way contains somewhere between 200 and 400 billion stars. Roughly half of them are similar to our Sun in size, temperature, and age. Stable, long-lived stars around which planets can form and stick around long enough for interesting chemistry to happen. We now know, from direct observation with instruments like the Kepler Space Telescope, which stared at a small patch of sky and counted planets hiding in the faint dimming of starlight, that most stars have planets. Not some, most. Planets are the default, not the exception. And most of those planetary systems include at least one world sitting in the habitable zone, that band of orbital distance where a planet's surface can hold liquid water. Liquid water is the one ingredient we know, from the only example of life we've ever studied up close, to be non-negotiable for biology. Everywhere on Earth where we find water, we find life. In hydrothermal vents miles below the ocean surface, in acid lakes, in frozen Antarctic rocks, in the upper atmosphere. Life on this planet has proven spectacularly adaptable to hostile conditions. The only thing it has never managed to do is survive without water. So wherever we find liquid water in the universe, we have at least a reason to ask the question. Now run those numbers, even conservatively. Even if only 1 in a million of those habitable worlds ever developed life, that's still hundreds of thousands of living worlds just in our galaxy. Even if only 1 in a million of those life-bearing worlds produced intelligence, something capable of building tools, having language, wondering about the universe, you still have hundreds of thinking civilizations in the Milky Way. And the Milky Way is just one of an estimated 2 trillion galaxies in the observable universe. 2 trillion. That number doesn't mean anything in everyday life. It's too large. But the implication it carries is clear, even with the most pessimistic assumptions about how rare intelligence is. The sheer scale of the cosmos should have produced minds in enormous quantities. The universe has had 13.8 billion years and an almost incomprehensible amount of space to work with. Life should be as common as stars. Here's what makes it stranger. Civilizations that developed even 1 billion years before us would have had 1 billion years to grow, to spread, to leave mark. 1 billion years is enough time, at speeds well within the reach of known physics, at a tiny fraction of the speed of light, for a civilization to populate every star system in the Milky Way, and then some. They wouldn't need faster than light travel. They wouldn't need to rush. 1 probe per century, building copies of itself from local materials at each new star, would be enough to fill the entire galaxy in far less than 1 billion years. The math doesn't require anything exotic. It only requires that the civilization wanted to expand and had long enough to do it. So there should be evidence everywhere. Signals, structures, modifications to planetary atmospheres, engineering on the scale of star systems. The galaxy should look, at some level, occupied. Instead, everywhere we look, nothing. Total, unbroken silence. The SETI program has been listening since 1960, when Frank Drake pointed a radio telescope at 2 nearby sun-like stars and waited. He heard natural noise. The project has grown enormously since then. Millions of stars surveyed across billions of radio frequencies. Searches for laser pulses. Searches for anomalous heat signatures. Searches for patterns in stellar light that couldn't be explained by physics alone. The universe has been examined with extraordinary care and increasing precision for signs of company. And the universe has, so far, said nothing. There was one moment, August 15th, 1977. A researcher named Jerry Eman was reviewing data printouts from the Big Ear radio telescope in Ohio. This was back when you literally looked at paper printouts, column by column, and he came across something that made him pick up his pen and write a single word in the margin. That word was "wow," with an exclamation mark. What he'd found was 72 seconds of signal, narrow band, exactly the frequency long predicted to be ideal for interstellar communication, arriving from the direction of the constellation Sagittarius. It was strong. It matched almost perfectly what researchers had designed their instruments to find, structured enough to stand out, coming from the right direction, at the right frequency, the right intensity. For about 72 seconds, Big Ear picked up something that looked unlike anything natural known to physics. Then it stopped. It was never repeated. Every attempt to find it again has come up empty. The wow signal remains, nearly 50 years later, unexplained. It wasn't confirmed as extraterrestrial. It wasn't confirmed as anything. It's an open parenthesis in the history of astronomy, not evidence of contact, but also not fully resolved. One anomaly in 60 years of listening. Everything else has been silence. This is the Fermi Paradox, named for physicist Enrico Fermi, who reportedly asked the question over lunch in 1950 while discussing UFO reports with colleagues. Where is everybody? Not as a joke, as a genuine scientific puzzle. The universe is old, enormous, and by every principle we use to understand chemistry and biology, should have produced minds in vast quantities. And yet the silence is complete. The standard explanations, the ones people tend to reach for first, are worth going through carefully, because each one sounds reasonable on the surface and starts to wobble when you look harder. The first is the rare Earth hypothesis. Maybe intelligent life is extraordinarily rare. Maybe the specific combination of conditions required, the right star, the right planetary orbit, the right axial tilt, a large moon to stabilize that tilt, a gas giant in the outer solar system to sweep away comets, a planetary magnetic field to deflect radiation, a mass extinction event at precisely the right moment to open an ecological niche for intelligence, is so improbable that it's effectively happened once in the observable universe. That we are, genuinely, a cosmic accident so unlikely it couldn't repeat. This is a logically serious position. There are biologists and astronomers who hold it. But it also requires us to believe that in 13.8 billion years across 2 trillion galaxies, The lottery came up winning exactly once. Here, now, us. Possible. Also deeply convenient, in a way that should make any honest thinker at least a little suspicious of their own preference for the answer. The second is the distance and time argument. Maybe civilizations exist but are simply too far away, or haven't had time to reach us, or are just beginning their own equivalent of the radio age while we're already looking. 60 years of radio astronomy is nothing on cosmic timescales. A civilization that lit up its radio emissions 50 years ago on the other side of the galaxy wouldn't have its signals here yet. That's fair. But remember the math about self-replicating probes spreading across the galaxy in under 1 billion years. Distance and time stop being convincing when you account for how much of both the universe has already had available. The third is the wrong frequency, wrong technology argument. Maybe advanced civilizations communicate through methods we haven't invented yet. Quantum channels, neutrino beams, something we don't have language for. Maybe radio waves are the cosmic equivalent of smoke signals, and every serious civilization moved past them so long ago that the idea of searching with radio telescopes is like searching for internet traffic by putting your ear to a telegraph wire. This is genuinely possible. It's also genuinely untestable, which is the frustrating catch. An argument that can explain any outcome, they're there, we just can't see them, doesn't help us understand what's actually happening. Each of these answers carries something real, and none of them closes the question completely, which is why, over the last few decades, a different kind of explanation has started getting serious traction. One that doesn't require exceptional luck or technologies beyond our imagination. One that follows from 2 observations about survival that would apply to almost any intelligence, anywhere, that ever existed long enough to become detectable. The possibility is that the silence is deliberate, that the universe might contain minds that hear us, or could hear us, and that the silence is a choice, a response not to nothing, but to us specifically. Before you dismiss that as science fiction, let's work through exactly why the logic isn't as outlandish as it first sounds. Start with an image. You're walking through a dense forest at night. You can't see more than a few meters in any direction. You don't know what else is in the forest with you. Animals, people, something you haven't accounted for. You have 2 choices about how to move. Light a torch and announce your position to everything in every direction, or move quietly and try to understand the environment before making yourself known. Most people, instinctively, choose silence first. Now stretch that instinct across an entire galaxy, across millions of years, across the survival calculations of civilizations that have been around far longer than we have. The dark forest hypothesis, developed in detail by Chinese science fiction author Liu Cixin in his trilogy The Three-Body Problem, but rooted in logic rather than narrative, is essentially that image, formalized into a theory of how intelligence behaves when it takes the long view of its own survival. 2 premises drive it. The first is that survival is the primary need of any civilization. Not happiness, not expansion, not scientific achievement, survival. Because nothing else is possible without it. Any civilization that has lasted long enough to become technologically detectable has survived long enough to absorb this lesson at a deep level. Whatever intelligence looks like on another world, the creatures who built it thrived because they prioritized their own continuation. That doesn't disappear when a species becomes sophisticated. It tends to become more strategic and more far-sighted with sophistication. The second premise is that the universe's resources are finite. Stars exhaust their fuel. planets are bounded in mass and material. The total energy available to any civilization, however advanced, is limited by thermodynamics. Civilizations grow. That seems to be what growth-capable systems do. But the space they grow into has ceilings. Follow those two premises to their logical conclusion. If two civilizations encounter each other across interstellar distances, each represents a potential future competition for the same finite pool of resources. This isn't about either civilization being aggressive or hostile. A civilization might be genuinely peaceful, curious, open, but it will also grow, develop more powerful technology, and eventually require more. Whether that becomes a conflict depends on circumstances that neither civilization can fully predict, because neither can predict the other's trajectory across thousands of years. Here's where the problem gets genuinely difficult. You cannot verify intent across interstellar space. A signal that says, "We mean no harm," is indistinguishable from a signal that says that and means something else, because you have no mechanism to test the claim. The distance is too vast, the biology too alien, the evolutionary history too divergent. You're being asked to make an irreversible decision. Trust or don't trust, based on information you cannot independently verify, about a civilization whose behavior 1,000 years from now you cannot possibly predict from today's communication. Game theory has spent decades studying scenarios like this, when two parties can each either cooperate or defect, and where defecting carries a catastrophic but survivable downside for the defector and a potentially catastrophic downside for the cooperator, and where there's no reliable communication before the critical moment. The rational tendency across many different frameworks and many different assumptions about motivation is toward the cautious, defensive option. The dark forest hypothesis applies this reasoning at a civilizational scale and across cosmic time. It's not a claim that intelligent life is malevolent by nature. It's a suggestion that the structure of the situation, finite resources, unverifiable intentions, enormous stakes, timescales measured in millions of years, might consistently push different kinds of minds towards similar behaviors. Stay quiet. Listen carefully. Treat detection of another civilization as a problem to be understood, not immediately celebrated. Think about what that implies for the silence. If this kind of logic governs even a fraction of the advanced civilizations that exist in the galaxy, the cosmic environment becomes something quite different from the welcoming place we've tended to imagine. Not hostile necessarily, just structured in a way that makes silence the rational equilibrium. Everyone is quiet because the cost of being wrong about contact is too high. A civilization that wants to shout into the universe is free to do so. But a civilization that has been around long enough to think carefully about what happens next might not. The scientific community is genuinely divided on this. This isn't a fringe debate held in the margins of astronomy. In 2015, a group of leading scientists, including researchers from NASA, MIT, and Harvard, published an open letter calling for a pause on METI, messaging extraterrestrial intelligence, the deliberate sending of signals. Their concern was not paranoia. It was precisely this, that before broadcasting our existence more loudly, we should think seriously about what responses are possible and whether we've thought through the range of them carefully enough. Stephen Hawking made a similar point publicly, and he was not someone given to rhetorical drama about science. His position was that while contact might go very well, the history of encounters between civilizations at different levels of technological development on this planet suggests caution is at minimum worth considering. He wasn't predicting catastrophe. He was noting that optimistic by default is a choice, not a conclusion. Others disagree. Jill Tarter, one of the founders of SETI, has argued that a civilization capable of interstellar travel would have had to develop cooperation and stability to get there, and that the projection of conflict-based logic onto extraterrestrial minds reflects our own anxieties more than any evidence about how intelligence behaves. Douglas Vakoch, who directs an active METI organization, argues that we've been radiating signals for 80 years already, and that deliberate messages are simply clearer versions of what the universe has already received from us. Both positions are serious. Neither is obviously wrong. What's striking is that the debate exists at all among working scientists, that the question of whether to keep announcing ourselves to the cosmos is considered genuinely open rather than obviously resolved. Because here's the thing, we have already been announcing ourselves, whether we meant to or not. The radio era began in earnest in the 1930s and 40s. Military radar systems, airport transponders, television broadcasts, FM radio, all of it radiates outward at the speed of light. A sphere of electromagnetic leakage centered on Earth is currently about 80 light-years in radius, meaning every star within 80 light-years has, in principle, been bathed in our signals for at least some portion of the last century. That's not a huge volume of space in galactic terms, only a few thousand star systems, but it's not zero either. In 1974, researchers deliberately amplified that announcement. Using the Arecibo radio telescope, then the largest in the world, they aimed a dense, structured transmission at a cluster of 300,000 stars called M13, about 25,000 light-years away. The message encoded prime numbers as a kind of mathematical handshake, a diagram of our solar system, the structure of DNA, a crude image of a human figure, and basic information about our technology level. It was specifically designed to be recognizable as artificial, something only a mind could have produced. Scientists were proud of it, and by every measure of scientific ambition and creativity, it was a remarkable achievement. 3 years later, in 1977, Voyager 1 launched with a golden record attached to its hull. Sounds of Earth, music from around the world, greetings recorded in 55 languages, images of human life, mathematical diagrams. Our location was encoded using the positions of 14 pulsars, which function as galactic landmarks stable enough over millions of years to triangulate a position. Any civilization that found the probe and had sufficient astronomical knowledge could work backward to identify the star system it came from. These were acts of optimism, expressions of the deeply human belief that the universe is a place where contact would be a gift. Whether that belief is correct, whether the universe rewards openness or treats it as something else, is precisely what we can't answer from here. What we can say honestly is this: the dark forest is a hypothesis, a carefully reasoned one, grounded in premises that are hard to argue with, but still a hypothesis. The silence it predicts is the same silence we observe, which means it fits, but so do other explanations. The universe being simply empty of other minds also fits the silence. A cosmos where everyone is genuinely trying to make contact, but the distances are just too vast, also fits. We can't distinguish between these scenarios from inside the bubble of our own observation. What we can do, and this is where the science gets genuinely creative, is look for the physical shadows that civilizations would cast on the universe around them. Not signals they chose to send, marks they couldn't avoid leaving. Here's a thought experiment. Imagine you're trying to determine whether a city exists in a remote region of the planet, but you're not allowed to land or make radio contact. What would you look for from a distance? You'd look for heat. Buildings and factories and vehicles generate thermal signatures detectable from orbit. You'd look for chemical anomalies in the atmosphere. A city of millions produces carbon compounds, nitrogen oxides, industrial byproducts that don't occur in those concentrations naturally. You'd look for light. Cities glow at night in patterns no geological process produces. You'd look for the modification of the landscape, roads, reservoirs, cleared land, the geometric regularity of agriculture. You wouldn't need them to signal you. You'd read the marks their existence left on the environment around them. The same logic applies to civilizations at the scale of star systems and galaxies. A civilization advanced enough to have survived and expanded for millions of years would be detectable not because it chose to broadcast, but because its sheer physical presence would alter the environment in ways our instruments might recognize. The most dramatic version of this is the Dyson sphere concept. Freeman Dyson proposed in 1960 that a civilization with sufficient technology and ambition would eventually build a structure, or more realistically, a swarm of structures, around its star to capture as much of the star's energy output as possible. The engineering details are secondary to the observable consequence. A star wrapped in energy, capturing material, would stop emitting normal visible light, and instead glow primarily in infrared, radiating the waste heat of whatever the civilization was doing with all that energy. The thermal signature would be distinct, detectable across enormous distances, and impossible to explain through any natural process we know of. We've looked for this, seriously, systematically. A survey called GOT, the Glimpsing Heat from Alien Technologies, examined data from about 100,000 galaxies, looking for anomalous infrared signatures that might indicate civilizations using a significant fraction of their galaxy's stellar energy. Another survey examined individual stars within the Milky Way. The results have been consistent. Nothing definitively artificial has turned up. Now, absence of evidence is not the same as evidence of absence, and that's worth being precise about here. We've examined a small fraction of the stars in the Milky Way. Our instruments have limits. A civilization that was extremely efficient at using energy might not waste enough heat to produce a detectable signal. There's real uncertainty in this search, and responsible scientists are careful not to overclaim from it. Still, the scale of what we've looked at and the completeness of the silence across it is striking. In 2015, a star called KIC 8462852, immediately nicknamed Tabby's star after the researcher Tabitha Boyajian who first flagged it, became briefly famous for dimming in patterns unlike anything seen before in stellar data. Normal planets produce small, regular dips in starlight. Tabby's star produced large, irregular, asymmetric dips, sometimes blocking more than 20% of its light, sometimes in complex, overlapping patterns. One astronomer carefully, cautiously, responsibly noted in print that orbiting megastructures were consistent with the data. The internet, predictably, exploded. Subsequent observation and analysis found more prosaic explanations, likely clouds of dust and cometary debris from disrupted objects in the system. The excitement faded, as it usually does. What remained was the demonstration that this kind of search is now a real scientific practice. We know what artificial megastructures might look like in stellar data. We're looking. The universe is, so far, not cooperating. There are other hypotheses about why we might not see advanced civilizations, even if they exist, and some of them are stranger and more interesting than the dark forest. The zoo hypothesis, proposed by John Ball in 1973, suggests that advanced civilizations know we're here and have collectively decided not to make contact, treating Earth like a nature reserve or a controlled experiment, maintaining deliberate silence to allow our development to proceed without interference. This is the benign version of structured silence, not hunters hiding from prey, but researchers observing without disturbing. It's an appealing idea because it imagines a universe full of minds and also explains our isolation without requiring threat. Its weakness is the coordination problem. It requires every advanced civilization to independently arrive at and maintain the same policy, with no defectors. In human terms, getting every government on Earth to agree on anything and hold that agreement for millions of years would be unprecedented. Whether alien civilizations would be more disciplined is, obviously, unknown. A grimmer variant, proposed by computer scientist and mathematician John von Neumann, and later developed by astronomer David Viewing into what's sometimes called the Berserker hypothesis, suggests that the galaxy might already be seeded with autonomous, self-replicating probes, not designed to make contact, but designed to detect and neutralize civilizations before they become a threat to whoever sent the probes. The probes replicate themselves across the galaxy using local materials, spread faster than any biological civilization could travel, and sit dormant until they detect a civilization reaching a certain technological threshold. The silence, in this scenario, is the silence before something wakes up. This is the science-fictional end of the hypothesis spectrum. It's taken less seriously than the others, and for good reason, but it's worth knowing it exists as a logical possibility that falls out of the same game theory reasoning as the dark forest. These hypotheses range from plausible to speculative, and the honest answer is that we don't have the tools yet to distinguish between most of them from the inside. What they share is a framework. The silence is not random. It means something, and what it means depends on which of these scenarios reflects the actual structure of the universe we're living in. Which brings us to the idea that has the largest stakes of any in this entire conversation: the Great Filter. The term was coined by economist Robin Hanson in 1998, and it refers to whatever it is that prevents intelligent civilizations from reaching the level of visibility we'd expect them to reach, given the numbers we started with. Something filters civilizations out, not by preventing life from starting necessarily, but by preventing it from becoming large, long-lived, and detectable. Something is doing this consistently across billions of years and an enormous volume of space, because the silence is so complete. The Great Filter might not be one thing. It might be several steps, each improbable, each acting as a partial bottleneck, their combined effect making visible civilizations rare enough to explain the silence. But the most important question about the filter, and this is the one that shifts the weight of the whole conversation, is not what it is. It's when. If the Great Filter lies behind us, if the nearly impossible step is already in our past, then we are survivors. Something in our history was so improbable, so contingent, so specific to Earth's exact circumstances, that civilizations almost never make it past that point. Maybe it was the origin of life itself, the first self-replicating molecule forming in a chemical soup 4 billion years ago. This transition happened only once on Earth, in the roughly 200 million years between when conditions became suitable and when the fossil record shows life present. It might be genuinely rare across the universe, occurring perhaps once per galaxy per billion years, or less. Maybe the filter was the jump from simple bacteria like cells to cells with a nucleus, a transition called eukaryogenesis that took roughly 2 billion years to happen on Earth, and may have required such a specific kind of cellular merger that it almost didn't happen at all. Maybe it was the development of multicellular life, or the emergence of sexual reproduction, or the evolution of a central nervous system, or the specific sequence of events that produced primate intelligence, rather than some other evolutionary branch. Each of these transitions was genuinely improbable in ways we're still trying to quantify. Any one of them could be the filter. If we've cleared it, the silence makes a kind of sense. We are extraordinarily early. The galaxy is mostly empty, not because of predators or catastrophe, but because the chemistry of intelligence is rarer than the chemistry of stars. We are, in this scenario, pioneers in a young and mostly lifeless cosmos. That's a strange kind of solitude, not threatening, more like standing in a vast, quiet landscape at dawn, before anything else has started moving. But if the great filter lies ahead of us, if the bottleneck is something civilizations hit after reaching our current level of development, then the silence becomes a record of failures. Every civilization that looked something like us eventually encountered something it couldn't survive. Not some of them, all of them, or close enough to all of them that the exceptions are invisible in the cosmic data set. What could that be? Nuclear and biological weapons are the obvious starting points, and they carry real weight because of what we've already demonstrated about ourselves. In 1945, we developed the ability to destroy our civilization in less than a century of industrialization. Since then, we've also mapped the human genome, begun editing genetic code with tools that become more powerful and more accessible every decade, and started developing artificial intelligence with capabilities that are growing faster than our understanding of how to align them with human values. The pattern: technology advancing faster than the wisdom and institutions required to govern it, is not unique to our civilization's specific moment. It might be a structural feature of how intelligence and technology develop in general. There's a more subtle possibility that doesn't get enough attention. What if civilizations don't tend to destroy themselves, but simply stop in a way that makes them invisible? Advanced enough to solve the problems that threaten survival, secure enough to become internally focused, no longer motivated by the outward expansion that would make them detectable, not dead, not hiding, simply elsewhere in their priorities, choosing depth over breadth, presence over expansion, experiences we can't currently imagine over the construction of megastructures we'd notice. In that version, the silence reflects not catastrophe, but maturation. Every civilization that gets far enough past our current point eventually turns its attention inward, and from the outside, it looks exactly like disappearance. This is the most humanizing version of the Great Filter, not a wall, but a door, leading somewhere we can't see from here. We genuinely don't know which of these is true. Say that plainly. We don't know. And more than that, we might not be able to know from our current position. A species a few centuries into industrialization, with instruments that have been searching for a handful of decades, trying to read a cosmic signal that might require millions of years of context to interpret correctly. What we can do is notice where we are in the possible sequence of events. We are a civilization that is, right now, navigating the development of technologies that have no historical precedent on this planet. Artificial intelligence, synthetic biology, climate systems we've already begun modifying without a full understanding of the feedback loops. We are doing this while organized into competing nation-states that have not demonstrated a reliable ability to cooperate on problems that require global coordination. We are doing it fast, faster than our social and institutional evolution has kept pace with. Meanwhile, we are broadcasting our existence into the cosmos as clearly and continuously as we know how. We did this not from recklessness, but from the best possible impulse: curiosity. The desire to find out if we're alone. The hope, deeply human and genuinely beautiful, that the universe is full of minds that would welcome contact. Whether that hope reflects the actual structure of the cosmos, or whether it's a form of innocence that the silence is quietly commenting on, that's the question that doesn't have an answer yet. Here's what's worth holding on to, though. The Fermi Paradox is not just a question about the universe. Every serious attempt to answer it eventually becomes a question about us. What kind of civilization are we? Where in the arc of development do we sit? Are we early enough to still shape the outcome, or are we already deep into a sequence whose trajectory is set? Are we the rare survivors of a filter that stopped almost everyone else? Or are we approaching something that has stopped almost everyone else after reaching a point that looks very much like where we are now? These aren't questions with clean answers. They're questions that live in the space between what we can observe and what we can only infer, which is, honestly, the most interesting space in science. The universe has been listening to us for 100 years. We've been listening back for 60. In cosmic terms, both of those clocks started about a second ago. Every night we add to the signal we're sending, and every night we add to the record of silence we're receiving. The most important thing about that silence might be that it's still unresolved. Not that it means anything definitive about threat or loneliness, or our odds of survival, but that it means we're still early enough in the question to matter, still in a position where understanding it and what it implies about how civilizations develop and what threatens them might actually be useful. That is genuinely worth paying attention to, not because it's frightening, but because the question of why the universe is silent is inseparable from the question of what kind of civilization we want to be. And that's probably the most important question we've ever asked. The sky is quiet tonight. It has been quiet every night humans have looked up at it. What that quietness is trying to tell us is still, after all this time, entirely open.